Light refraction is the change in the direction of light as it passes through different transition mediums. Different transparent objects will refract light differently, so it becomes one of the more reliable ways that we can identify transparent crystals and gemstones. In this video, I will demonstrate the basic use of an instrument called the refractometer and how it works. We are most familiar with light refraction when looking into or out from water. Our eyes might see something in water, but the light ray has changed in direction as it passes from the water to the air, meaning that what we are actually seeing is a virtual image and the object is in a different place. The measure of light refraction is called the refractive index. Different transparent substances have a known refractive index, which is what we can measure using a refractometer. A refractometer, like this one, has an eyepiece and a place at the back where we need to place a light source. This one has a purpose-built torch which attaches to the back, which makes it very handy and portable. When we open the lid of the instrument, we notice a gem table and a rectangular area which is the surface of the prism inside, where we're going to place the gemstone. One limitation in getting a good reading from this instrument is that we need to be able to place a flat surface on the prism. I'll explain a little bit later how we still might be able to measure a curved surface, but it's really designed for taking a reading from a cut gemstone. If it's set in jewellery, we may still be able to get a reading as long as the surface of the gemstone can make contact with the prism. At the surface where a light ray passes from a dense substance like water into something less dense like air, the light ray is refracted at a known angle. This depends on what's called the angle of incidence, and the angle of refraction is always greater. As the angle of incidence increases, there comes a point where it reaches what's called the critical angle, when the refracted ray is 90 degrees from normal or straight on. If the angle is made any steeper, the refracted ray will no longer even pass from the dense material, but it will become totally internally reflected. This is precisely how the refractometer measures the refraction. It actually measures the total internal reflection of the light ray. But first, one more point about this light source. The more accurate refractometers will pass the light first through a monochromatic filter. We could still use white light, but we will get a more precise reading with only one colour of the spectrum. We can think of this like a smaller paintbrush making a more accurate line than a wide brush with lots of colours at once. So by taking white light and selecting only one particular frequency, we can get a more precise result from the instrument. Historically, this yellow light frequency became the standard because it is the light given off by salt burning in a candle. So the precise measurements are based on this frequency, so it's best to use this exact yellow colour. So inside the refractometer is a very clever design which uses precisely placed mirrors to direct the light ray towards the gemstone at the critical angle, by first passing it through a prism which is denser than what the gemstone is going to be. Some light will be refracted through the gemstone and some internally reflected back into the refractometer, but first through a scale, then bounced off another mirror through the eyepiece to our eye. So as we look into the eyepiece, we can see that part of the reading scale is darker, which is the light that has been refracted off into the gemstone, and the lit up area is the light that has been reflected. The refractive index is read directly from this scale. The shadow line represents the critical angle between the prism, which is a known density, and the gemstone being tested, which is variable. Now looking closer at the top of this prism, one more thing is required. We need to use a fluid called a contact liquid. We need to be very careful because it's quite toxic. This fluid has a known refractive index itself and is needed so that the gemstone can make optical contact with the prism. Otherwise the readings won't be accurate. So the fluid creates a kind of a seal so that it's only the gemstone being measured and not the gap in between. The trick is to use a very small amount. It's almost the smaller the better, and we need to be very careful at this stage. Many instructions and tutorials on applying RI fluid suggest that you actually drop it onto the gem table first and then slide the gem through the fluid onto the prism. This is mainly because the prism actually has a relatively low hardness, even less than the fluid if it crystallizes. So we must not scratch the prism when we clean it, or with the gemstone, or with tweezers, or the instrument is going to become ruined because it will start to give false readings. So we really need to be careful with anything that makes contact with this part of the refractometer. So the way to get a really accurate reading is to start to write down exactly where the shadow falls on the scale, taking measurements with the stone at a few different positions. When we're finished, we should take a soft tissue and carefully wipe away the fluid so that we can protect the prism. Looking through the eyepiece, we need to move our head up and down, and the shadow edge will move as we do this. As we move our head up and down, we should write down the highest values that we see, then check this with the stone in different positions. It's harder, but not impossible, to take a reading from a cabochon or a curved surface. We do this by using a very, very tiny droplet of fluid and then positioning the stone on the fluid. If we can manage to have the droplet appear on the scale, we can use what's called the distance method, looking from about 30 centimeters above the eyepiece, moving our head until we see the droplet half dark and half light. We can get an idea of the refractive index by doing this, but it's not as accurate as using a flat surface. We can start to write down the readings through the eyepiece, but some refractometers also include a polarizing filter, which we can unscrew and place over the eyepiece. Now, most transparent gemstones are doubly refractive, meaning that the refracted light is actually split into two rays. The difference between these two rays is called its birefringence, which can also be measured with the refractometer. So with a doubly refractive stone, there will be quite a range of readings as we move the gemstone around. We then move this polarizing filter back and forth 90 degrees. This does a couple of things for us. Firstly, if the shadow edge shifts abruptly as we move this filter 90 degrees and back a few times, it shows that it is indeed doubly refractive. If the shadow edge stays still, it's singly refractive. Secondly, the polarizing filter makes things easier because we can then take the highest and lowest positions one at a time as we move the stone. Instead of listing very different readings around the stone, we can eliminate one at a time and do the readings separately. So after taking readings in a few different positions, we can see what the RI range is of the stone and also work out its birefringence. By comparing these figures with the known details of gemstones, we can very likely work out what the stone is. Even more information can be taken from the refractometer if we still can't decide between two possible identities of a stone. By carefully analysing the movement of these shadow edges, we can decide whether the stone has one optic axis, uniaxial, or two optic axes, biaxial. Also, whether it has a positive or negative optical sign. This has to do with the two refracted rays and which one is refracted more and which less. This is probably more complicated than the scope of this video, but just be aware that by studying the movement of these shadow edges, we can find out even more about the stone than just the refractive index range, if we really need to.